Lesson 13. So in the previous example, we have looked at the binary example that we're using the binary search, and which will return the index and the word separately, right? So why not we use as a structure for that as well? Because the index, the word as well as the counter will always come along, right? So here is a version which we will let our binary search to return our key structure directly instead of like last time we let it to return the index only. So here you should understand the one change is we first need to assign the type of this function, right? This is our binary function. The type of its return is a pointer pointing at a structure called key. Okay. Also, we will need to declare another pointer, which is to hold the return value from this function. So this is the one main change. And the remaining change will be happen inside this binary search. We will see it in a little bit, but the rest of the function, the logic of the function are the same, right? So you keep getting those words in. If it's a letter, you do something to increase the count of it, right? And after that, you print it out. So that logic is the same. Let's look at this binary search function, which using the pointer now is a return. So it's again, the biggest change here is the return type is become the structure as well. Before it is an integer, I believe, right? Now, we also want to define those low, high, mid point is the pointer as well. Again, before they're in integer, serve as an index. Now we're using them as a pointer to point at a particular structure inside our structure array. All right, for example, the low one, we're pointing at the first one, high pointer, pointing at the last one, the middle pointer, we will point it at the middle point, which we'll figure that out later quickly. So inside the while loop, typically we will have our middle equal to low plus high divided by 2, right? But we cannot do this here. Anyone can tell me what's the reason we have to write this way rather than simply adding the low and high and divided the result by 2? So why we want to use this complex version? Like previously, in the previous example, the middle equal to bracket low plus high end of bracket divided by 2, right? We previously do that, but now we change it. Why? Any thoughts online? No? All right. So anyone tell me what's the type of low and high here?
Structure.
Yes, it's a structure, but be more specifically, it is a pointer pointing at the structure, right? Yeah. So you cannot actually adding 2 pointers together. It does not make sense, right? Pointer is a value of your memory address. Adding 2 addresses together like means nothing, right? However, you can minus 1 address by another that means the difference between those two addresses, right? And then you divide that by 2, that means half of the distance, and you add that on top of the low address. So you reaching the half point address in the memory between those two values.
Why we don't just use the differencing sign to be able to do low plus high divide by 2?
Yeah, low plus high, low and high here are two address.
No, I mean using the differencing sign, the star, to make sure that we get the value inside the reference.
We don't want the value here. Yeah, because this is a pointing at a structure. So yeah, you made a very good point. So imagine in your memory. So let's see. Okay, let me share this window. So let's imagine this row number is our memory. All right. So remember, our structure will have two things inside. One is the word itself, right? For example, the word is the keyword, which is break, right? The second value is the count of it, which is 0, right? Another word will be what is that? And for example, another value. And let's try one more. Say for loop, right? That's another counter. Okay, so we are using a pointer pointing at address, memory address 1 right now. That makes sense so far? This is our low pointer. It's pointing at number 1. All right. And then the other pointer is pointing at high, which is the last entry in our array, which is 5. All right. And first of all, we calculate the difference between those two addresses, which is 5 minus 1 will give you 4, right? You divide that by 2, then you got 2, and you add the 2 to the 1, you will get the middle point. That's the pointer you point in the middle. All right. So again, you can think, okay, why not I just directly calculate the 3 by adding 1 plus 5, I will get divided by 2, that will get 3, right? But remember, if your address is way bigger than, could be way bigger than this. And again, like the biggest thing is this is operation is not allowed in C. You cannot add in two memory address together. Because inside your C, the memory address are storing as like a 16-bit or 32-bit. You cannot adding two 32-bit together. It will cause overflow, right? You will need a special type of data to store an even longer memory address. The memory address in the memory often comes like, for example, 10010011, something like that, like 8-bit. The other memory address is like 1001, like this, right? If you're adding those two memory together, you will lose something at the beginning, right? And that after you do the division, you are way off comparing to the original value you want to track.
Okay, I got it. And the other solution I was thinking of is maybe add the two address together and divide by the size of the structure.
Again, adding them together will causing the overflow I just mentioned, right? That's not, yeah. Divided by structure of size of structure could work, but again, the adding part will not work.
Okay.
Yeah, because you see, adding those two numbers together, you will need 9 bits, right?
Mm.
Yeah, which is not allowed in your computer hardware. You cannot store the address longer than 9 if it's an 8-bit system. All right.
So the solution will be maybe to divide each of them by the size of the structure, and after adding it together.
No, not either. Like the solution is the one I showed in the slides.
Okay.
So you will calculate the differences first, then you add that difference on top of the lower end value.
Thank you.
Yeah. Okay. So yeah, again, the solution is you have to calculate the difference first, and then you divide difference by 2 and add it to another address. That is okay, because the difference is the offset. Okay, so yeah, so we have talked about a few changes here, right? Like first change is our function type will be changed, and then we have this low and middle and high type also change to pointer. We calculate the middle point. Then we compare the keyword in the middle point versus the keyword, the word we just read in. And that the following process is very similar. If they matches, we will return the middle, right? But here, the middle again is not an index anymore. It is a pointer pointing at a keyword inside the keyword table. All right. So one thing is that the size of the structure sometimes is a little bit hard to predict, even you knowing exactly what is the variable inside your structure. For example, in our previous case, we have a character array as well as an integer, which is obviously hard to predict because you don't know how long that array will be. Even so, say you knowing that there's one variable is a floating point, another variable is a double, another variable is integer. You don't want to calculate the size of structure by adding up each of those variables. It not necessarily works. You can directly using a function to calculate the size of the structure directly. Okay, that is fine, but not separately and adding them up. That will not work. Similarly, if you're having this pointer pointing in the structure and you use plus plus, it will automatically calculate for you the shift in your memory, enough shift in your memory to reaching to the next value. So that is automatic. But yeah, when you're trying to get the size of the structure, you need to use a function for that. I will show you a little bit later. Before that, let's look at an example of completing the same process using Python. If anyone ever learned Python, so it's very simple as 6 lines. First of all, you open the file. Secondly, you break the string inside the file into words using the split. And then you create a dictionary, and then you finally keep adding the word into your dictionary. All right. So this function will do two things. One is if it's there, it will add the count of it. Otherwise, it will add the word into the dictionary and assign the count as 1. And finally, print out everything. Right. So previously in the C version of our program, we use like almost 3 pages of code. Right. Here in Python, it's only 6 lines. So you can see how much difference it is This is all because everything has been handled internally, especially using this dictionary function. Right? Inside using the dictionary, you can search for the word directly just by having this bracket and the word. It will automatically give you that count value position, right? Rather, in our case, we have to use the binary search to find it. So actually, in Python, the dictionary object is written, well, everything is written by C, but dictionary object is written by C using more than 3,000 lines. So just to help this, to create this special function, structure in Python, it will handle the pointer and the memory automatically for you. The other thing is that when we talk about our binary function, we will declare a function in this way. It might be a little bit confusing to see what is this actually means, because you have this pointer in the middle, and after that you have some brackets. I mean, depends on the person. Some may think this is hard to read. So alternatively, you can break the line like this. It will still work. If you prefer this way, you can do that. Okay. The biggest benefit is you can see the function name much easier. This is your function name, right? Versus this way, it's a little bit hard to figure out what is actually your function name is. Okay. Now we're going to use the structure to make linked list as well as the binary tree. We have already learned that in the data structure course, so I'm not going to teach you the basic about those, but only to show you how to implement it in C. So here, the first example we'll look at is the doubly linked list, which means you will have a structure including where the previous item is and the next item is, right? This is very useful because this gives us opportunity to expand our list on the runtime. You can add in as many as you want to the list. For example, if we're reading a file and we want to store every single line of them separately in a structure, well, before we open this file, we don't know how many lines is inside of it. So it's, well, we could estimate, say, set maximum line, right, as we did before, but the linked list will give us the opportunity to dynamically expand it. So here is the example. So we have this node, right, linked list node defined, which has these character array to store the line of the text, right? The other two things will be a link to the previous node and the next node, right? Note that the type of those two pointer are also the structured link node. Okay, so they're the same type, right? This structure here is the same as structure here, but here we just a pointer, right? So that's why we can take it. If you instead have another structure is a variable, that is not allowed. Okay, pointer is okay because you only store the pointer here. So let's see how it works. Let's say if we wanted to store reading a file and break it into lines, save them into a linked list, and at the end, we will print those lines in reversed orders. Okay, so this is our goal. So first of all, we will define the structure as we just saw. Then we begin our main function, and first of all, we will define three node: head node, tail node, and current node, right? Head and tail are new at the beginning. The current will assign that later, okay? And then we have this character array to store our input line. So we use a function to read this line from the input file. Okay, don't worry about it. Just assume that we'll be reading. And then we wanted to store this line to array, okay, to a character array. But here we wanted to set an accurate size of this array. Like the array size will be exactly as we need, rather than as we did before, we're using the maximum number, right? We don't do that anymore. We will first knowing how long the line is, and we're adding 1 to it. Anyone know why we add a 1 to it? Any thoughts? No? No one want to give it a try? Okay, I have too many candy here. Please help me out. Okay. So the idea is we want to allocate enough memory for this new line, right? So we knowing how long our input line is, and then we add a 1 for the new terminator at the end. So we allocate that much of 1 extra spot as the type of character, right? And then we assign that memory to this character save pointer. Okay. Then we use a special function to copy over the line into this save, because the line was saved in an array, right? And we want to save that into a different address. So we use a function to copy it over, basically copy every single character inside of it. So now we have this line in our save pointer. Next, we will create a structure as a linked list node. So this is how you create a structure. First of all, you want to allocate the right size of the memory to this pointer by using the size of structure pointer. So this is how you estimate the size of your structure correctly. Again, do not do the size of each variable inside and add them up. That will not work. Only using this way. And then you allocate enough memory based on that size, and you cast the type of that memory to the structure type, right? And then you assign that to your new node pointer. Okay. The reason we do that is because we have to assign those 3 things separately, right? We cannot create that in one shot. So we initialize it first, then we assign those values separately. So then we assign the text to the save array, and we assign the next to the new, and we assign the previous to the tail, right? So that by default, it will be at the end of your list, right? And then we check if there's anything in the head already. If there's nothing, our new pointer will become our head of our linked list. If there's already something in our tail, right, and that means we will override the tail. Our new list will become the new tail. But before that, we want to store the location of it. That means the current tail's next pointer will pointing at our new node. All right. Then we override the tail with our new one. Again, if you need a clarification of this linked list, let me know. Otherwise, I will assume that you have learned it. I won't go too much detail into it. So using this while loop, you will adding up each line one after another. So now at the end, we're going to print out those lines one by one, right? So by printing them out, we're starting from the tail, right? So we start from the tail. Every time we go to the previous node, right? As long as it's not to the new, and then we just print the text from the pointer, right? So if we want to do the other way around, let's say we're printing this list in the forward direction. So we can start with the head, and then we always go to the next in our list, right? And then we print out the text. So same idea. Okay, the next example we want to look at is the binary tree. The binary tree is another type of list. We can use that actually for our counting the keyword example. So let's see how it works. First of all, we define this structure for the binary tree. Similar to the last time, we have a text, we have a pointer to one thing and a pointer to another thing, but here are pointing at the left child and the right child instead of previous and next. In addition, we want to store the count of this word, right? Because that's the purpose of our function, which is to storing the number of words as well as the word itself. So this is how you define the structure. Again, like last time, this is called recursive declaration, means inside your structure you're calling yourself. However, again, you can only call the pointer of it, not the structure as a variable. Okay, now let's see how it works. So we will have a function, we'll get the word, all right, from somewhere. Don't worry about it, from some input. If the type of the word is a letter, we will add this word into our tree. Tree start with a new, which means nothing, but later on it will grow, obviously. So the tree function is the most important one, obviously. It's kind of determining where this word will go, right? If you still remember the binary tree, the order of how you insert this child node, right? Start from the left side and go to the right side, so on and so forth. So let's see that part a little bit. So this is the adding node to the tree function itself. So first of all, we will input our original tree. This is the original tree, and this is our new node, right? And original tree is a tree, sorry, as a structure array, and the new node is just a word. So first of all, we'll initialize a new node, right? This is our new. Well, before we remember we used that function to allocate the memory space for this new node. We kind of save it into a function now to make our code a little bit easier to read. We'll show you that later. And then we will have our structure initialized, right? Initialize that node by assigning the word by this word array. Initialize the count as 1. Initialize the left and right pointer to new because we haven't decided where it should go yet. Okay, then we will compare the new word versus the existing pointer and where it is pointing at. So note that this is the case that is the pointer is not new, right? So in that case, we'll compare. And if it's equal, we'll only increase the count without adding any node to the tree. If it's smaller, then the existing node, we will move it to the left side of our tree, right? So how to do that is, first of all, we will pass that node into another tree function. Then the tree function will return the position of this new node that will save into our left pointer. Otherwise, we'll save it to the right pointer. So using recursive method, we build this tree one step by another. And again, we compare the word inside of our tree. If at the beginning is nothing, so we just save the initial word. If they're equal, we only increment the count. If it's smaller than the existing word, we'll move the new node to the left side of the tree. If it's bigger, we'll move it to the right side of the tree, right? So that's how the binary tree works, right? So let's look at this tallocate function. So this is just a helper function to allocate the memory space. Similar to last time, we use a function like this to allocate the space for the node. This is you might notice that we have additional declaration step. This is because that's for the old style C language. In the new world, you don't need that line. You don't need this line anymore. You can simply just declare the memory like this. Okay. So finally, we're looking at this how to print out this tree, right? So that's just the bottom part. Also, we're using the print tree function recursively. So we only pointing at the tree if it's nothing on the left, then we print it out. Then we go print out the right side of the tree, right? So then it determines the order of the result. We'll always print out the left side of the tree because we're going to another recursion of this function. It will determine again if it's a node to the left until you reach the most left hand side of your tree. Then you print it out, print out the count, and print out the word. Then you go back to the parent node to print out each of them separately. So this way we'll make sure the word we print out are following the alphabetical order. There are some other things you learn from the other class, data structure class. This tree, well, we need to maintain the balance of the tree, otherwise it will take a very long time to search. One way will be using the AVL tree, but again, that's not covered in this class. All right, let's go with some exercise. We have two exercises. First one, we will show you the answer. The second one will be one of our next assignment question, assignment 4-1. Okay, so we'll look at this one first. In this question, what we want to do is we will still read a bunch of words coming together. And the difference is we want to group those words if the first 7 characters of those words are identical. Okay, I will give you some example. This is a little bit hard to understand. So let's say this is our input. It's like a snip of our code, right? We declare a bunch of functions. This is, again, input into our function is like a text file or string. Then what we want to do is we want to print anything if we have a few variable share the same beginning part. Let's say this variable 1, variable 2, and variable extra. because the first 7 letters of those variables are the same, we want to group them together and print them out. All right, so that's how we want to do it. Essentially, what that means is when you are making your tree, right, you only consider the first character, 7 character, when you determine if it will go to the left side of the tree, right side of the tree, or stay in the node, right? If you stay in the node, you will append that into your